Wanted to thank Professor Merab Kiladze for this opportunity to speak about the AIRGOS project. It stands for Artificial Intelligence, Genomics, Radiomics, Oncopathics, and Surgiomics. It's a project that utilizes, as you can imagine, artificial intelligence. So this is just a general overview of artificial intelligence surgery. We have machine learning, which basically is an algorithm that is created that is able to solve things that it wasn't necessarily programmed to do. Deep learning is a type of architecture, that a way that the algorithm is created. It has multiple layers, similar to the human neocortex, but it is essentially just another form of machine learning. But it's able to answer much more complex questions than straightforward machine learning. Computer vision uses deep learning to analyze visual data, and that's very important for surgiomics, which we'll talk about a little bit later. And lastly, we have robotics and artificial intelligence surgery, which incorporates elements of artificial intelligence, computer vision, as you can see here. Yes, and I should mention virtual reality and augmented reality are also aspects of computer vision. So we talked a little bit about artificial intelligence in surgery. Examples of that are simulators using virtual reality, postoperative detection of complications, that's an example of machine learning, data acquisition using natural language processing. That's a very, people have been working on this for decades. It's surprisingly difficult to do to get quality data. Another example of AI in surgery, preoperative decision support, such as cyst surveillance of pancreatic cysts. You can do projects using natural language processing, which will look through doctors' charts to pick up cysts, maybe from CT scans that people aren't thinking of, and helping people get the proper surveillance they know, essentially autonomously or automatically. And then computer vision. There's many examples of that, but I don't have time in my talk to talk about that. But they're beautiful images of augmented reality and virtual reality, which I'd love to show you, but we don't have time. So this is another example of artificial intelligence in surgery. This is a review article, Decision Support in Surgical Oncology is a systematic review. Here's another example, looking for postoperative complications after hepatobiliary and pancreatic surgery, again in our journal. And lastly, this is from Professor Hashimoto's group. He's now at the University of Pennsylvania, and he's really one of the leaders in artificial intelligence research at this time. So I encourage you to look at those if you're interested in this topic. So what about the AIRGOS project? All right, this was actually the cover of our last issue. So this is just the title of the paper. A lot of the topics I talk about, you'll be able to find in this paper. So if you're interested, I encourage you to go there. So omics. Omics comes from the Greek word for whole. So we have genomics, or a study of the entire genome, radiomics, or a study of all the images from, say, a CT scan, not just a few slices. We have pathomics, again, that's looking at all the images, the pathology slide images, looking at all the immunohistochemistry, all the different stains, everything, not just looking at a couple to come with a diagnosis, but really all of it, and looking at it down to the pixel to a level that the human brain can't comprehend and the human eye can't see. Of course, without a microscope and moving a microscope around quite a bit. So using this concept of the whole, surgeons have been starting to talk about surgiomics and what that is, and we'll talk about that a little bit later. So genomics, it's important to remember that the entire human genome, it seems surprising how long ago it was, but it was characterized entirely back in 1998, and it's now readily available. And you can now do a test to get a whole genomic sequence for about $1,000 to $2,000, which is pretty mind-boggling when we think of how expensive the Human Genome Project was to where we are today, that we can do a tumor for just a couple of $1,000s. So because of this, we started to get the idea for AIRGOS. Radiomics, again, we talked about this, where all the radiologic images are analyzed instead of just a single image or a very limited number of images. and you really need a deep learning architecture to interpret this visual data. Okay, and it's very powerful already, radiomics, which we'll see again in a little bit. Pathomics, uh, really, we talked about this again. You can look down to the pixel, you can look at all the different stains, and you can look at much more data, again, than the human brain can comprehend. So surgiomics. Essentially, surgiomics is the study of surgery. Surgery is not just in the operating room, surgery is before the operating room, surgery is after the operating room. So the concept of surgiomics is actually incorporates aspects of radiomics, incorporates aspects of pathomics. Really, we call it integrated surgiomics when you try to integrate all the available patient data that influence surgical outcomes. Okay. Now, specifically in the operating room, you can talk about visual or video surgiomics. You can record the operation, and the computer can analyze all that data, again, to a level that the human brain can't. We just don't have enough time in a day. But there's a lot of data, again, looking down to the pixel. We can maybe pick up more tumors. We can maybe pick up more complications. We can maybe stage people better. And in addition, we have things like biophotonics or ICG, or hyperspectral imaging, narrowband imaging, and multispectral imaging, which are being used more and more in the operating room. And again, all these different settings. Imagine the entire operation can be analyzed by a computer. And so that's an example of video surgiomics, which is really an interesting new field, obviously for us in surgery, but also for endoscopists when they're doing colonoscopies and endoscopies, bronchoscopies. They can record that data and they can get essentially many more answers. You can imagine this being used obviously in ultrasounds also when you have recordings of ultrasounds being done. So we'll talk more specifically about the AIRGOS project. We chose the term AIRGOS because I work here in Georgia now, and of course the legend of Medea. We already had some Greek references with Asclepion. Trident. I actually went to the Medea Museum and I found a picture of Jason chasing Medea and he's holding a trident. So anyway, that's a little side note. So this again just looks at the current cancer treatment flow. We have imaging, we have biopsies, we have surgery pathology, and then we know what we based on that we do a tumor board and we try to guess essentially what will be the best chemotherapy for people. But the reality is we don't need to do that anymore. We can look at the whole human genome. Obviously, it's expensive now, but it's getting cheaper and cheaper. And as we create these algorithms, which is what the AIRGOS project is, we hope to be able to do this workflow, run this algorithm for people. So what do we mean by that? Again, we're going to look at all the radiographic images. Specifically with CT scan, we're going to look at the preoperative CT scan, pancreatic protocol of all patients with pancreatic cancer. We're going to get a biopsy. We're going to do the whole genomic sequence from a biopsy from an endoscopic ultrasound or what have you. Or if we have to, postoperatively after it's been removed, we're going to look at the histopathology, all the images, and we're going to look in retrospectively first what patients lived more than 2 years, what patients lived less than 2 years, and we're going to try to, by categorizing these two different types of patients, we're trying to see what patterns exist, and hopefully we'll be able to predict better what chemotherapy people should get, what immunotherapy people should get. Maybe the timing will be a different type of timing that we haven't thought of. Maybe they should get immunotherapy, then surgery, then chemo, or maybe they should get surgery, then radiation, then chemo, then immunotherapy. Who knows? We're hoping that the algorithm will be able to tell us better. So where did we really get this idea? This came from actually my friend Professor, part of this, at least the radiomic part, came from my friend Professor Takeaki Ishizawa at Osaka University. They did a study looking at patients with hepatocellular carcinoma. They looked at a single arterial phase CT scan, and they split patients up. Whether they were resectable or not was not the issue, but they looked at patients just on this single image, and they were able to teach an algorithm retrospectively and then go forward with new patients and accurately predict on a single image which patients can recur in 2 years, which patients are not going to recur in 2 years. This dramatically changes how we do surgery. As surgeons, we only think if a tumor is resectable or not. But we have the technology today to realize whether we should remove the tumor or not. If a radiomic algorithm can tell us that the tumor, sure, it's resectable, but it's going to recur in 6 months, that's valuable data for us to know, and we wouldn't operate on these patients. Again, this technology exists, we're just not utilizing it. So now we're not using whole genomic sequencing, we're not using radiomics. Now imagine adding pathomics, imagine adding surgiomics data. We start to have a very powerful algorithm and truly personalized medicine. So this is that paper by Professor Ishizawa's group I was telling you about. If you want to read about it, again, they're looking at a single slice. Imagine when you look at the entire 3D reconstruction of that tumor, how much more data we're going to get. Exciting. It's going to take a supercomputer. It's going to take a lot of money. But luckily, it looks like we can overcome that. So these are the universities that we're going to do the first trial of AIRGOS. We have a university in Brussels, University of Magdeburg, Germany, a hospital in Italy, Poliambulance in Brescia, University of Padova in Italy, and the University of Osaka in Japan. So the goal of AIRGOS is to use every possible data point to create truly personalized medicine for cancer patients via a deep learning algorithm that combines visual and non-visual data. The first tumor study will be pancreatic cancer. If this model works, we will move to colorectal, liver metastases, and renal, lung, and beyond. And this paradigm could theoretically be used for non-malignant diseases such as inflammatory diseases and endocrine. Again, we could look at pathomics, genomics, we could look at everything again, and it could dramatically change how we do medicine in the future.
If you enjoyed the video, don't forget to hit the like button, share it with a friend, and subscribe to our channel, Intuitive Search. Thank you for watching.